Welcome, dear students. So, in this course, Introduction to Finite Element Method, C5203, today's topic is Mathematical Basis of Finite Element Method. Now, first let us see why do we need to study the mathematical basis. The reason is you have derived or you have seen the derivation of bar element, and that derivation was based on the mechanical interpretation of an axially loaded bar. Okay, so for example, I think you remember we first took the bar element. It has two nodes at the ends, two-noded bar element, and each of the node has 1 degree of freedom. So we are numbering them by 1 and 2. These are my degrees of freedom. And a stiffness term defined as Kij as the load developed at degree of freedom I, force developed at degree of freedom I due to unit deformation at degree of freedom J. So it's, I hope you remember, it's pretty easy to remember rather. Just like I and J are in alphabetic order, similarly R and S are alphabetic order. So I is the receiver R and J is the source S. So the unit deformation is given at jth degree of freedom and the effect is studied at ith degree of freedom. Okay. So therefore, my K11 means the force generated at degree of freedom 1 due to unit deformation at degree of freedom 1. Now, based on these definition of stiffness terms, now we can find out if I have a force applied, force P, at one node of the element of length L, okay, where all other degrees of freedom are restrained. So we're fixing it, the second degree of freedom we have fixed. And then my force divided by area, if the area of the element is A, then stress is P by A. And if the deformation is delta, then I know that strain will be delta by L. And based on linear elasticity, we know that stress by strain is Young's modulus or E. And therefore, what we can write is stress divided by strain, so P by A divided by delta by L or multiplied by L by delta gives me E, and therefore P by delta is obtained as AE by L. Okay, so K11 is my AE by L, and you know that when I will have this force, the reaction at degree of freedom 2 will be in just opposite direction. Therefore, K21 will be minus A by L. Similarly, when I give unit deformation at degree of freedom 2, by releasing this and by fixing this degree of freedom 1, I will have again this force will be negative, so minus A by L, and here it will be K22 will be again A by L. So ultimately I get the stiffness matrix of the bar element as A by L times 1 minus 1 minus 1 1. This you are already familiar with. You must have used this in solving bar problem or truss problem earlier by converting this local stiffness matrix in the local direction to the global direction. So we are not going to discuss all those things here. Now the point is, this element stiffness matrix for a bar element we have derived on the basis of the mechanical behavior of it. Now this process is not possible to be applied in order to find the stiffness matrix of all types of elements. Okay, because this kind of simple expressions simply may not be available for a complicated element, say a four-noded quadrilateral element, rectangular element, okay? And therefore, we must be able to find a general method to derive the element stiffness matrix of any type of element, okay? And that is why we need to understand the mathematical basis of the finite element method. And in that sense, we can visualize the finite element method as a numerical tool to solve the partial differential equations. All right. Now, why partial differential equations? Because you know from your knowledge of physics or mathematical physics that most of the physical phenomena like mechanical behavior of various bodies or thermal behavior or wave propagation or diffusion phenomenon, etc. All those can be expressed in terms of some partial differential equations. You must have studied some of those in your mathematics course. Now the problem with these partial differential equations is that their solution is not possible to be obtained by analytical methods, by pure rigorous mathematical methods for complicated domain and boundary conditions. That means if my geometry is complicated, if my boundary conditions are complicated, then analytical solution of those PDEs are not possible. We can find analytical solution only for very simplified cases, okay? But real engineering problems involve complicated geometries, complicated material properties, and complicated boundary conditions. And therefore, we need to solve these partial differential equations numerically. And the finite element method is one of the most commonly used numerical method to solve those different partial differential equations for realistic systems where my geometry may be complicated, where my boundary condition may be complicated, or where my material properties may be complicated. All right? And that is why when we look at FEM as a numerical tool for solving partial differential equations, then it becomes necessary to understand what is the relationship of FEM with those partial differential equations, how we can use the FEM to solve those partial differential equations. Okay? So that's why this topic is important, so that once we understand those mathematical techniques, it is possible for us to derive element stiffness matrix of any kind of element, whatever we may be able to use in a realistic engineering problem. Okay? Now, before we directly go to finite element method to solve those partial differential equations, we need to learn a little bit about various methods, numerical methods or approximate methods, not numerical, but approximate methods to find the solution of partial differential equations. And two most commonly used such approximate methods for solving partial differential equations are, number one, Galerkin's method of weighted residual, we call it. This is a very common method. And the other method is Rayleigh-Ridge method. All right? Now, in Galerkin's method, what we do, the partial differential equation or the differential equation is converted into some equivalent integral equations. We will see how it is done, and it is actually not difficult to understand. You will realize after we take up the problems. Then what we do, we assume certain approximate solution for those differential equations. We need to assume certain approximate solution, and those approximate solution comprises of one or more unknown parameters. For example, I may take the approximate solution as a polynomial of the independent variable. Suppose, for example, say I have some quantity like say deformation as a function of x, and this I may take as a linear polynomial, say a0 plus a1x, or I may go for a quadratic polynomial, say a0 plus a1x plus a2x square, and so on. Okay. Now, in this approximate solution, mine is a0 and a1 are my unknowns. Okay. Now, when I take these approximate solutions, then since it is an approximate solution, it will be different from the exact solution, the true solution. And that difference between the exact and approximate solution is called residual. It's basically error, okay? And that residual, we try to minimize that value of the residual so that our approximate solution can give me the best possible answer, which is close to my exact solution, most closed one to the approximate solution. That's why we try to minimize the residual, and in that process, while minimizing the residual, we are able to find out equations from which I can find out these unknown parameters like a0, a1, etc. And once I get these values of parameters, I can finally fit them to the approximate assumed solution. Okay, so obviously my solution will be approximate, but the error between the approximate solution and the true solution will be minimum. All right, and that's how we can arrive at the approximate solution in Galerkin's method. All right. Then the other approach is Rayleigh-Ridge method. Here what we do, we define an equivalent functional which governs the physical problem. Like say for any mechanical problem, say I can find that the potential energy, okay, due to the deformations caused by the loads. That will be my functional. And you know that potential energy is minimized for equilibrium by any body, any loaded body, and therefore by minimizing the functional, we are able to find out the solution of the partial differential equation or differential equation. So these are the basic premises of these two methods, Galerkin's method and Rayleigh-Ridge method, in order to find the approximate solution of our partial differential equations. Then once we understand the method, then what we'll do, we will cast those methods in a form which becomes amenable, which becomes easier to bring into the finite element form. Okay, so we'll cast those methods in a manner so that we can easily find out the finite element stiffness matrices. And in order to illustrate all these, we will take up a very simple problem of axial deformation of a bar to illustrate these methods. We are taking a one-dimensional problem so that the method remains easier to understand and the fundamentals becomes clear. Okay, so let us take up a bar under axial deformation, and for that what we do, it may be a general kind of bar of any shape. Of course, its other two dimensions will be quite small compared to the axial dimension. That's why it is a one-dimensional member, one-dimensional body. And what do we do? Suppose this is my axial direction. The axial direction, we are denoting it by x, and the bar is acted upon by some surface force which varies with x as well as with time, where x is the location of any point along the axis. Okay, so x is the independent variable. X and t are the independent variable by which we denote the position of a point within the space, and t denotes the time associated with that position. All right. And for a general bar, if the material is non-homogeneous, then modulus of elasticity may be a function of x again. So I am writing it as E of x. And area, if it is not uniform bar, then area will vary along the axial direction, and therefore A is also a function of x. Okay. If my material is homogeneous, then Ex will be just a constant, which is E. Okay. This surface force may be of any kind. In FEM terminology, we call them surface traction. Suppose you have a pile, then you know that there will be frictional side friction on the pile. Okay. And that can be visualized as a surface traction. Okay. So it's a function of x and t again. So Qx t. Okay. Now let us consider a small portion of the bar, and let us consider a free body diagram of the portion. So we are considering a length of dx of the bar, and we will try to find out the equilibrium of this infinitesimal bar element, portion of bar. Here element doesn't mean finite element. Okay. Now, because it is a time dependent problem, we are assuming that our independent variables are functions of both position and time. Therefore, the material, the body might undergo some acceleration. If it is a dynamic problem, that means. Okay. And we are calling it U double dot x and t. Because U is a function of x and t, U double dot means double differentiation of U with respect to time. Okay. So the number of dots indicates the number of differentiation with respect to time. So U dot means du dt, U double dot means d2u dt2, which is nothing but our acceleration. Okay. Now in the free body diagram, we see that in this phase I have a force F, and since force will obviously be a function of x and t at any time t, it will be a function of x. Therefore, in the other direction, I have F plus del F del x into dx. There's my force. And then due to this acceleration, there will be some inertia force also. As per Newton's second law, this inertia force will oppose the net force acting on the system. And therefore, if acceleration under the net force is acting towards right hand direction, therefore this inertia force will act towards left hand direction at any instant. Okay. And therefore I am showing this acceleration force towards the left. Now therefore I can now write down the equilibrium of all these forces, and in that case what I get in the left hand side, my total force is force, this F plus the inertia force mu double dot. So I have added them. And in the right hand side, I have F plus del F del x into dx plus Qx into dx. So now I can find out the mass of this element as rho times the volume, and volume is area times the length. Therefore, rho Ax dx is my mass. And when I put those expression in the equilibrium equation and doing this simplification, I get rho Ax into U double dot is equal to del F del x plus Qx. Okay. Now what I can do is I can use the material properties of the bar, because we know that force is the area times the axial stress at that point. Therefore, Ax times sigma x. And also I know from linear elasticity that sigma x is E times the normal strain, that is epsilon x. And epsilon x I can express in terms of U as this del U del x for small deformation. Okay, so higher order terms are neglected because it is small deformation. And therefore finally I can write F as E times Ax into del U del x. I am using homogeneous material here for simplicity so that E is a constant, not a function of x. If the material is non-homogeneous, then again this will also be a function of x. E will also be a function of x. All right. Then by using these values in the equilibrium equation, what I can find is that equilibrium equation is given by this: rho Ax U double dot equal to del x of E Ax del U del x plus Qx. Now you see this equilibrium equation is a second order partial differential equation both in time and in space. Here I have second order time differentiation U double dot, and here I have del x of del U del x. So again second order. So the equation is a second order partial differential equation both in space and time, and therefore we will need two initial conditions and two boundary conditions for its complete solution. The initial conditions can be specified as initial displacement and velocity. So at time t equal to 0, the bar may have certain initial displacement or certain initial velocity or both. In most of the time, if the system starts from rest in a dynamic condition, then we assume this initial displacement and initial velocity to be 0 for most of the realistic problems. And then these boundary conditions, which is boundary condition means it depends on the space, okay, spatial variation. So this will involve specified displacement or the first derivative of the displacement at the ends of the bar, at the boundaries. All right. Now you see the specified displacement will be at displacement boundary condition, all right, whereas specified derivative of displacement, because it is related to strain, and strain can be related to stress and finally force, therefore the derivative of displacement that is ultimately related to applied force at the boundaries. All right, applied force at the boundaries. So therefore, suppose my bar has a length of L, say bar has a length of L. In that case, at L equal to 0, say let me consider a bar, say having an area, say it's a prismatic bar, and say I have its length as L, okay, its length as L, and it has an area A. Area is A, which is constant. E is constant. So x is 0 here, so I will call x equal to 0 at this end and x equal to L at this end. Then if this end is fixed, say if this end is fixed, then I can say that U at x equal to 0 for all time is 0. Okay, and then if I have a say force here, say P, a tensile force, then what I can say is that I can express P at x equal to L is nothing but my del x of E into A into del U del x at x equal to L. That is my P. Okay. So I can either specify displacement or double derivative of displacement in terms of the force. Okay. So this P, if it acts for all the time, then I can call that P at L and T is equal to Cp. So that's how I can have either displacement boundary condition or force boundary condition. Okay. And if my problem is a static problem, if it is not a time varying problem, then this term will just cancel and everything will be a function of only x. Okay. In that case, the partial differential sign will change to total differential because it is a function of only one variable. Am I right? And therefore, what I can write is that for time invariant problem, for static problem, my equation simplifies to ddx of A E du dx plus qx will be equal to 0, right? So here in this case, that means my partial differential equation, instead of the partial differential equation, I get a ordinary differential equation. Okay. Now, in order to specify the forces, etc., we need to follow certain sign convention. So let us list the sign convention. So sign convention is that if the applied force is in the direction of the positive direction of the axis, then it is a positive force. Otherwise, it is a negative force. Say, for example, let me draw a bar once again. Say I have, this is my bar and it has a length of L. Okay, it has a length L. Sorry, it has length L and it has a constant area A and it has a constant material property E. And I am taking the axial direction towards right as the positive. Okay, say this is my axis and this is my positive direction of x. In that case, if I have a force at the end, say this P, this is a positive force. On the other hand, if I have a force here, this is a negative force because it is acting towards a negative direction of the axis. So that's how we take the sign convention. Therefore, if I specify a force at the left hand side of the bar, okay, in that case I will have P at say x naught equal to 0. Actually I can take this as the position of x naught and this as xl, then P x naught is a negative quantity, so A E into du dx, area into stress at x equal to x naught. So this is a negative quantity. Okay, so this is how we take up the sign convention. Now let us note a few important conditions or important points regarding the boundary conditions. You see, this problem of axial deformation of a bar is a second order differential equation if it is static. If it is dynamic problem, then it is a second order partial differential equation. And therefore, if we want to integrate analytically this second order ordinary differential equation, it will give rise to two integration constants, right? And therefore, at least two independent boundary conditions must be known or specified for a unique solution of the problem. Now, one thing should be very clear, that we need to avoid rigid body motion of the bar for solving the problem, because if the whole bar moves in space, no stress strain, no deformation takes place. So it is not an non-trivial solution for us. Therefore, in order to avoid rigid boundary body motion, we must have at least one displacement boundary condition specified. Say at one point the displacement is 0 or something like that, or some value. The other boundary condition may be either displacement boundary condition or a force boundary condition. And you know that force and displacement boundary conditions are interrelated through the material behavior. And therefore, we cannot specify both the boundary conditions at the same time. I cannot specify a displacement boundary condition and also a force boundary condition at the same point, because they are not independent from each other. Okay? Actually, what happens if I specify some displacement boundary condition at a particular point, say displacement is 0 at some point, then it will involve some unknown reaction. If the displacement is known, that force is not unknown for me. It can be obtained only after solution of the problem. So these conditions must be fulfilled while specifying the boundary conditions. Okay? Now, with this background, let us go for exact solution of the axial deformation of a bar, okay, of a uniform bar, okay, uniform homogeneous bar. So now let us take up the exact solution of a prismatic bar under axial deformation. So this is my bar of length L. It's a homogeneous prismatic bar, so area is constant throughout the length, which is A. Since it is a homogeneous material, so I have its elastic modulus as E everywhere, and it is a fixed at one end, and there is a force, concentrated force at the other end, which is P, and the surface traction force is a linearly varying load. So Qx is equal to Bx, where B is some constant. Okay. And therefore, for this problem, my boundary conditions are that U at x equal to 0 is 0, and at this x equal to L, my force I can express in terms of u again using this. So AE du dx equal to P. As per sign convention, this is my positive force, so it is P. All right. Now coming to the ordinary differential equation, we know that it is ddx of AE du dx plus qx is 0. Since A is constant, so I take it outside. So AE d2 u dx2 plus bx, qx is bx equal to 0. All right. So for solution, let us solve it by integration. So if I integrate it, therefore what I get is AE du dx, if I integrate it once, plus b into x squared by 2 will be equal to C1, right? C1. And if I integrate once again, integrating again, integrating once more, I'll get AE into U plus B x cubed by 6 will be C1 into x plus C2. So these are my two integration constants whose value we must find out from the boundary conditions. All right. So therefore I can find out the value of u as u will be equal to 1 upon AE multiplied by C1x plus C2 minus bx cubed by 6, right? Bx cubed by 6. Now at x equal to 0, u is 0 from the first boundary condition. So if I put x equal to 0 here, this term will vanish. X equal to 0, this term will also vanish, and right hand side, left hand side is 0, so therefore C2 must be 0. So u0 is 0, that implies C2 is 0. Okay. And now I know that from my first boundary condition, I know that AE du dx is P, so I must be able to find out now du dx by putting C2 equal to 0. So let me write u is equal to 1 upon AE into C1x minus bx cubed by 6, and therefore what is my du dx? Du dx will be 1 upon AE into C1 minus, this will be twice x square, so it will be bx square by 3, right? Bx square by 3. And now at x equal to L, du dx is what? Du dx at x equal to L is 1 upon AE into C1 minus BL square by 3. Okay, and therefore AE into du dx at x equal to L will be how much? Let me write it here itself. So AE into du dx at x equal to L is my P, hence C1 minus BL square by 3 is my P, and therefore C1 is P plus BL square by 3, right? And therefore now by using this value of C1 in the original equation, in the solution, what I can write U equal to, hence from this equation, by putting value of C1 here in this equation for U, and C2 is already 0, I know, therefore finally I'll get U is equal to 1 upon AE into C1 into X, so thrice P plus PL square by 3 is my C1 into X plus minus BX cube by 3. Okay, and therefore if I simplify again, I'll get I'll get I did some silly mistake here, of course. So integration of this will give me thrice x square divided by 6, so it will be bx square by 2. Okay, I had written earlier 3, so please kindly note this error. And from here, by putting the boundary condition value, I get finally C1 equal to P plus BL square by 2. And when I put this value here in this equation of U is 1 by AE into C1 is P plus BL square by 2 into X. So this I have simplified as 2P plus BL square by 2 into X minus BX cube by 6, and then after simplification we get U equal to this. Okay, and we can further simplify it. So we can write here it as, if I divide everything both top and bottom by 2, I will get 6P plus thrice BL square minus BX square whole thing into X divided by 6AE. So this is my value of U in terms of X. And we see that this U varies cubically with X, because the highest order of this term is X cube. All right. Now, if the bar is not carrying any surface traction, say B is 0 in that case, then what do I get? If I put B equal to 0 here, then my U for no surface traction, B is equal to 0. And in that case, I'll have U equal to, U will be equal to 6P into X by 6AE. So Px by AE. And therefore U at X equal to L will be PL by AE. This is a well-known solution. We have already seen in the beginning that when you apply the load P at the end, the deformation and the load is PL by AE. And that's how we got stiffness as A by L. Okay, so this is a well-known solution. So it means our solution is all right. Our solution is all right, correct, because it is giving me back the well-known result. Okay, so this is how we can solve the differential equation of equilibrium exactly, and thereby we get this well. Okay, now let's go for finding the same thing, the axial deformation of the bar, using Galerkin's method. All right, using Galerkin's method. So as we discussed already, in Galerkin's method, what we do is we try to fulfill the governing differential equation in an approximate manner, as we have already discussed. So let us see an example of this Galerkin's method in for the bar problem, deformation of bar, axial deformation of bar problem. And let us write the differential equation of equilibrium first. You know that the differential equation we had got as ddx of AE into du dx plus qx, and we had already assumed q as linearly varying function. So let me directly write here b into x in place of q. So b into x is equal to 0. And what are my boundary conditions? I know that this equation is fulfilled. Say my bar starts at x equal to x naught, and it ends at x equal to xl. In that case, what I can do is say this is my bar, and here my x is x naught, and here my x is xl. So I may have either displacement boundary condition or force boundary condition in these ends. So therefore my BCs can be at x equal to x naught we may have either u equal to u naught, okay, or I may have, since my force will be in the opposite direction, therefore minus AE into du dx. This is my force at x equal to xl, okay, at x equal to xl is say P naught, if I have a force here as P naught. All right, so I may have either a displacement boundary condition or a force boundary condition. And similarly in the right hand side at x equal to L, at x equal to xl, I may have either u equal to ul, or I may have force equal to PL, which is, this time it will be positive, AE du dx at x equal to xl is PL, okay. Say I have a force PL here, which may be simply P also, just to indicate that it is at the final point XL. We are writing this suffix XL, and this is a mistake on my part. This should be x equal to x naught. All right, so these are my boundary conditions. Now we call this as weak form, this Galerkin's method or even Rayleigh's method. We call them as weak form because the solution does not fulfill the actual solution at every point, okay. Therefore we call it weak form of solution or approximate solution. So in the weak form, what we do is we assume an approximate solution. All right, so Galerkin's weak form, let us find the weak form of the equation now. Weak form of the equation. So what we'll do is we will assume an approximate solution. It will not be same as U, the true solution. So we may call it, say, U tilde. Okay, U tilde. And this approximate solution, usually it is assumed, it may be of any form, it may be any function of x in this case, but usually polynomial form is more preferred. Okay, so U is a polynomial in X most commonly. All right. Now this assumed solution, this U tilde, must contain unknown parameters. Unknown parameters. This I have already discussed. Say the coefficients of the polynomial may be those unknown parameters. All right. And then these unknown parameters are obtained by minimizing the difference between the exact solution and the approximate solution. Unknown parameters are determined by minimizing the difference between the true solution and approximate solution. That means between U and U tilde. All right. Now suppose let us take an nth order polynomial C for this approximate solution. So let's assume U tilde to be some polynomial, say A0. It must be a complete polynomial, A1x. We'll discuss why it is so, why we need a complete polynomial, say A2x square, and like that up to an x to the power n. Okay. Now in general, since it is an approximate solution, this solution will not fulfill the differential equation at all the points within the domain. That means between x0 and xl. This is my solution domain between x0 and xl. So here my solution domain is here x0, x lies between x0 and xl. This is my solution domain. Now this U tilde or the approximate solution will not fulfill the governing differential equation at every point in the domain between x0 and xl. Okay. So in general, U tilde won't satisfy the ODE. In this case it is ODE. In some other case, time dependent problem, it may be PDE, or in a 2D problem it may be a PDE, etc. Okay. The ODE will not satisfy the ODE at all points. At all points within the domain. All right. And when I substitute this solution, approximate solution, in the governing equation, then I will have some error of the governing equation. Let me call that error as E, and therefore when approximate solution u tilde here is substituted in the governing ODE the error will be, say I call it E, which is a function of x, because my u tilde is not fulfilling the actual u at every point, so that error will depend on the independent variable x. So this error is actually will be equal to ddx of AE du tilde dx plus qx, and this obviously will not be 0. Had this be actual u, then my governing equation says that this sum is 0, but since it is not the actual solution, it is the approximate solution, therefore it is not equal to 0. Okay, and this total error over the solution domain, over the domain is called residual. Okay, and now what we'll do, so total error will be given by what? It will be given by integration of this Ex, right? Integration of this Ex over the solution domain. So my total error or residual Et, which is residual, is my integration of this Ex over the solution domain, Ex dx, right? Now if I integrate in order to find this total error or the residual, if I directly integrate it, then what may happen? In some point the error may be positive, in some other point the error may be negative, and therefore there may be cancellation of the error terms, and we don't want that. By cancelling it may become 0, okay, or it may be very minimum by cancellation. So in order to avoid this cancellation of error, what we do is we multiply this residual by some weighing function. We call it weighing function. Okay, and in that case, that weighted residual, I equate it to 0. I want that weighted residual, that means weighted total error, I want to be 0. Okay, and that's why this method is also called weighted residual method. All right, so what we do to avoid positive and negative error cancellation, we use weight functions or weighing functions. Okay, and then we want the total residual to be 0, weighted residual to be 0, and therefore what we write is say x equal to x naught to x equal to xl integration of this ex times weighing function ix dx is 0 for all i's I equal to 0, 1, 2 up to n. This number of I will be same as the order of the polynomial we have used. Okay. So this equation is called weighted residual equation. All right. So this equation we will call weighted residual equation. Let me box it. This equation is called weighted residual equation. All right. And this weighted residual is also called the weak form of the governing equation. This is also called weak form of the ODE. That's how we convert the differential equation to an integral equation. Okay, weak form of the ODE. So we must remember one point, that although this total error is 0, this approximate solution U tilde does not satisfy my ODE at every point, and that's why it is called weak form of the solution. It is not strong form. Strong form is the analytically or rigorously true solution, which is U, which we have already found out for this problem by integrating the original differential equation. Okay. So next, let us see how we can define different types of weight functions. Okay. So one method that is well known is called least square weighted residual method. Okay, in solving this weak form or the Galerkin's method. Okay, so one method is least square least squared weighted residual method. All right. So in this method, what do we do? We square the error terms so that it becomes a positive quantity, and sum of that square is equated to 0. All right. So what we do is E total, it is squared weighted residual. So E total is taken as the integration of E square dx equal to 0 over the solution domain. If it is from 0 to L, I can write the integral from 0 to L. Or if it is from x naught to xl I can write in the same manner accordingly. All right. Now, the necessary conditions for satisfying this least square weighted residual is that I will minimize the total square error, and therefore what I will do is I will need to satisfy the necessary condition. What is my necessary condition? Is that partial derivative of this total residual with respect to those unknown parameters must be 0. Okay? And therefore we'll write del et del ai, which says my twice integration of 0 to L E del I del AI into dx must be 0. Okay, because it is E squared. When I partially derive it, then I get 2 del EI del AI when I derive with respect to AI, and this is true for equal to 0 to n. Okay, so therefore what becomes my least square weighting function? You can see this is a constant, so this cannot be 0, so this must be 0, and therefore if you compare this with the weighted weighing function, this becomes my weighing function, and so weighing function becomes simply this del E del AI, right? Therefore in this method this weighing function Wix is none other than del E del AI. Okay, for I equal to 0 to n. So weighing functions are simply the partial derivative of the error terms with respect to those unknown parameters. Okay. So in the least square weighted residual method, what we have done, we have taken the weight function as the partial derivative of the residual with respect to the unknown parameters. Now there is one more method which is more popular for finite element formulation. Here what we do, the weighing functions are defined as the partial derivative of the assumed solution itself. So things become more simpler now. So what we do, we define my weighing functions as, say, Wix is defined as del U tilde del AI. Instead of error, I use the approximate solution directly for all i's equal to 0 to n. Okay, and this is more commonly known as Galerkin's method, and therefore the Galerkin method, when I use for all these I values of I, n values of I, then I will get this equation of total weighted residual equation, which says my from x naught to xl, integration of the error times the weighing functions. My weighing functions are none other than del u tilde del ai dx equal to 0. Okay, for I equal to 0, 1, 2 up to, and so I will get these n numbers of equations, using which we can finally find out the values of these unknown parameters itself. This we will see in next few minutes, right? How we can find it. So these are my weighing functions. So this is another important equation, and this is my residual equation in Galerkin's method. Right. Now, if I use this method, Galerkin's method, it is found that in many engineering applications, using this method gives me same results as that given by the other method, Rayleigh-Ridge method. So this method is quite commonly in use in FEM formulation. All right. Now, in this method, how to handle the boundary conditions? Let us see that. How do we handle the boundary conditions? So, handling of BCs. So, in applying the boundary conditions, we use the method of integration by part. Because my integral equation is involved and it has integration of product of two functions, therefore we need to apply the integration by parts, and for that we use this identity, which is well known. You must have been familiar with this in your calculus classes. So we use this formula for integration by parts, say from x naught to xl, integration of, if I have integration of ddx of a function fx multiplied by another function zx dx, then this is given by the product of these two functions at the boundaries. That means f of xl into z of xl minus f of x naught into z of x naught minus integration of same domain x naught to xl. Now my integration order is reversed. It will be ddx of zx, the second function, into the first function dx. So this is an important identity which is commonly useful in solving by Galerkin's method. Now, what is the advantage of this identity? You see, the right hand side contains the boundary terms. Since we already know the deformation boundary condition or force boundary conditions, so we can apply them in this identity. So that is one advantage of um, using this identity of integration by parts. All right. So if I apply this integration by part, or if I apply this weighted residual method to our problem, then what I will have? I will have this thing, integration of, sorry, let me change the color, integration of x naught to xl ex into wi x dx is what? Is my what is my error? Error is the weak form of the equation, right? So I can write ddx of AE into du tilde dx, okay, the dx of this whole thing, plus qx, whole thing multiplied by the weight function wi x dx will be 0 for all i's I equal to 0, 1, 2 up to n, right? Or if I separate these two terms, this term and q term, then I will get integration of x naught to xl ddx of AE du tilde dx into wi x plus integration of x naught to xl qx into wi x is my 0, right? Ix dx, I'm sorry, I must write this dx, I'm very sorry, for all i's, okay. Now this second order derivative within the integral sign I can write using this identity of integration by parts, okay. So this first integral contains second order differentiation of two functions, and therefore I will use now the formula for integration by parts, and in that case what I will get, I'll get, by doing integration by parts, I'll first write down the boundary terms. So I will have, you see here a and e are functions of x, and that's why I have put within the ddx sign. So if I write the boundary terms, then I will get the first integral value, I will get a at x equal to L into E at x equal to L, XL, okay, into second function du tilde dx into the weight function wix minus a at x naught into E at x naught into bu tilde dx into wix. These are my boundary terms. And then what I will have? I'll have minus integration of, now my order of differentiation will change. So ax ex into du tilde dx into ddx of this second function. So dwix dx, right, into dx x naught to xl. This is my first term when I use integration by parts, plus the second term as it is, plus integration of x naught to xl. This is x naught qx wix dx, and this must be 0, right? Clear? So for our problem now, what is this? This is my force boundary condition, right, at x equal to L, which I can say as PL. If my force at x equal to L is PL, I think we have shown earlier somewhere. Let me go back. Yes, these are my forces. So I can write these things in terms of those force values. So therefore from here what I get this term as PL, right, into WI into XL, WIX is not it, at x equal to L, minus P naught into WI at x naught. So these two terms have been written here in terms of force boundary conditions, okay. Then I have this third term. This third term is minus integration of ax ex du tilde dx into dwix dx from x naught to xl, okay, into dx plus integration of qx wix dx. This is my 0. So you can see now that the force boundary conditions can be naturally incorporated very easily, because this is defined as my boundary force from the material property, material behavior. And that's why these force boundary conditions are called natural boundary conditions, or simply NBC. Right? So the force boundary conditions, let me write fully, since force boundary conditions, FBC I'm writing, force boundary conditions can be incorporated naturally so force boundary conditions are called natural boundary conditions, natural BCs. In short we call it NBC. Okay. On the other hand, if my displacement boundary conditions are specified at the ends, then there is no direct way to fulfill those displacement boundary conditions in the approximate solution. And therefore, the approximate solution assumed one must be such that it satisfies the displacement boundary conditions automatically by definition. And that's why my displacement boundary conditions, DBCs, are called essential boundary conditions. Essential BCs, okay, or EBC. Remember, these BCs cannot be fulfilled later. It has to be fulfilled during definition of the approximate solution itself. That means when I find out the approximate value of U tilde, it must be such that it automatically fulfills the boundary conditions. Okay? And there may be n numbers of such approximate solutions which will be fulfilling these EBCs. And all such approximate solutions which fulfill essential boundary conditions are called admissible solutions. Okay? So the solutions which satisfy EBCs are called admissible solutions. Let me change the color. Admissible solutions. So we have learned quite a few new terms. One is the essential boundary condition, the other is the natural boundary condition. We have learned what is weak form of the solution, what is total residual, okay, and what are weighing functions. And in Galerkin method, the weighing functions are taken as the partial derivative of the assumed approximate solution itself. And the approximate solution which is to be used, they must satisfy the essential boundary conditions by definition, and therefore only admissible solutions we should take as the approximate solution while solving the problem. Okay? Now, one more interesting point is that Since the weighing functions are the partial derivatives of the assumed solution, we have already seen this. You see, in this Galerkin method, the weighing functions are the partial derivative of the assumed approximate or admissible solution itself. Okay? Therefore, if I use an admissible solution, then all the partial derivatives, that means the weighing functions corresponding to the location of essential boundary conditions, must be 0. Okay? Is not it? Otherwise, my essential boundary conditions will not be fulfilled. Okay? Since essential boundary conditions are some constant values, therefore their partial derivative will be 0 at those points. And therefore my weighing functions, values of weighing functions at the location of essential boundary conditions must be 0. Therefore, let me write this point also. This is an important point, that since the weighing functions or weight functions are partial derivatives of admissible solution, therefore at the location of EBCs, location of essential boundary conditions, the weight functions must be 0. Is it clear? Because the essential boundary conditions are some constant values at those locations. So their partial differentials must be zeros. And hence, we have to deal with the boundary conditions in this method in this following manner. Okay? So I will write down how we need to fulfill the boundary conditions in a tabular form. Okay? So in order to handle the boundary conditions, this table shows you the boundary condition term, then their specified values, the boundary term in weak form, and what are the requirements to be fulfilled by the assumed solution, and what is the type of BC. First, let us consider a forced boundary condition at the left hand end of the bar. As you know, because force will be a positive force will be in the negative direction of the axis, so this is a negative term, minus a at x naught, e at x naught into du tilde at x dx at x naught is my p naught, and the boundary term in the weak form will be that value multiplied by the weight functions, and the assumed solution need not fulfill any requirement for that, and therefore because this is an NBC, is a natural boundary condition, so they can be fulfilled naturally. Similarly, this is the right hand term, the force is PL, and this is a positive term, and the boundary term is PL into the weight function, and again it is a natural boundary condition, so assumed solution need not fulfill any requirement. I'm sorry. Then in case of essential boundary condition, say the boundary condition deformation at x equal to x naught is specified as u naught, then there will not be any boundary term in the weak form, and that boundary condition must be satisfied by the admissible solution itself, because it is an essential boundary condition. Similar is the case for the right hand side essential boundary condition. So these are the ways we need to fulfill the boundary conditions. The most important point we remembered is that the essential boundary conditions must be satisfied by the assumed solution itself. So only those solutions which satisfy EBCs are taken as admissible solution. That means that solution I can consider for solving the problem. Okay, now let us see this weighted residual method in terms of the principle of virtual work. So we have got this weak form for this axial deformation problem having force boundary conditions. Okay, this we have already got. Now what I will do, I will bring this term towards right hand side, and the other terms will be in the left hand side. In that case, what I will get is, I can write like this: these boundary terms minus this is equal plus this term is equal to 0. Then I will take this term towards the other side. That means it will become positive. So, and I am writing this as E times du delta dx into ax into this term into dx, integration of this. Okay, this term can be written as this, and then this must be equal to the sum of these three terms, this and this. All right, now let us interpret, let us assume that these wi x are my virtual displacements given to the structure, to the domain. In that case, what I can write? I can write that this Ex into this du tilde dx is my stress, right? Because this is string and this is my E, so this is my stress. Okay, so E of x into du tilde dx is my stress, sigma of x. All right, this multiplied by A is what? This multiplied, let me keep it as it is. Then what is this? If Wi is my virtual displacement, then ddx of that is my virtual strain. So I can visualize this dwix dx as virtual strain. This V stands for virtual of x. Okay, in that case this integral means what? This left hand side, therefore this left hand side is my integration of over the domain, integration of stress, true stress into virtual strain into ax dx, and this ax dx is v, ax dx is dv, so this is the volume integral of product of stress and strain, right? Stress and virtual strain. And this is nothing but my total internal work done by the virtual displacement over the body. So this is my total virtual work done. Now what is meant by the right hand side then? This right hand side, this is force into virtual displacement. This is also force into virtual displacement. And this is also integration of the surface force into virtual displacement. So this is my work done by the externally applied forces over the virtual displacements. So right hand side gives me virtual work done by the external forces. Virtual work done by external forces. External loads. And this equality shows that the internal virtual work done is same as the external virtual work done. So virtual work done internal is equal to virtual work done external. And this is my principle of virtual work. So virtual work principle. And therefore, since this virtual work principle is a very popular philosophy and method of finding solutions in structural mechanics, therefore, this Galerkin's method of weighted residual, since it is expressed in terms of virtual work principle, therefore, it is a very popular method in formulating finite element method. Okay, so that's why this Galerkin's weighted residual method is one of the very important and very commonly or extensively used method of finite element formulation, particularly in mechanical problems. Okay. Now remember, when we look at in this form, remember that these virtual displacements, that is the weighing functions, must also satisfy the essential boundary conditions. And that point we have already discussed earlier also, because since these weighing functions are partial derivative of the assumed solution itself, and therefore they must fulfill the essential boundary condition by definition itself, by definition of the admissible solution itself. So here again we see that these virtual displacements, which are weighing functions, must fulfill the essential boundary conditions. So that way the weighted residual method is interpreted as basically the principle of virtual work, and this is a very popular or extensively used in structural mechanics, used principle in structural mechanics, and that's why Galerkin's weighted residual method is one of the important and extensively used methods for formulating finite elements. So okay, with this we come to the end of this lecture. In the next lecture we will take up some example of actual application of this weighted residual method to solve the axial deformation problem of a bar. Okay, thank you.